sponsored by the Department of Health and Human Performance and the College of Human Sciences. I'm Jerry Thomas, Department Chair and Professor. This lecture is supported by the Pease Family Scholar Endowment, which was created in 1991 in the Department of Health and Human Performance in honor of Harvey and Bomo Pease from Newport Beach, California. The endowment was developed by their son, Dr. Dean Pease, and his wife, Sally, while Dean was a professor in the Department of Health and Human Performance at Iowa State. Dean was chair of the department from 1987 to 1990 and died in 1994. Sally is still an active supporter of the lecture and the department, despite living outside Iowa now. We're pleased for this year's Pease Family Scholar to welcome Dr. Eddie Coyle, Professor of Kinesiology at the University of Texas and the 14th Pease Family Scholar. Dr. Coyle spent the day visiting with various groups on campus, including faculty, staff, undergraduate students, and graduate students, and will do so tomorrow too. He was also guest this morning on Today in Iowa on WOI, our local NPR station, and did a video interview with KCCI later this afternoon. I'm not sure whether it made the 6 o'clock news tonight, but I think it'll make the 10. I believe he will also be in our department all day tomorrow. At this time, I would like to introduce Dr. Doug King, Professor of Health and Human Performance at Iowa State, who will introduce Dr. Coyle.
Thank you, Jerry. To apologize because I had a PowerPoint presentation prepared that had some gag shots of Eddie. So I see a lot of my students in here tonight, so you'll see them on Monday, Tuesday, Wednesday. No. So I'm doing this from memory now. Eddie graduated, I won't give the years because I don't really remember them, but he graduated from Queens College in New York with his undergraduate degree. His master's degree was at Ball State University with Dr. David Kostel, something that Dr. Rick Sharp and I share with him. And his PhD was done at University of Arizona with Dr. Jack Wilmore. And after that, he did a postdoctoral fellowship with Dr. John Hollisey. And all of these scientists are really world-renowned and three of the biggies in science. And as Eddie said today to my class, John Hollisey really started exercise biochemistry. So he had excellent training, and from there he has been a faculty member at University of Texas. One thing that is really impressive is, if I remember it right, you got tenure in 3 years. Is that right? Yes, which is very unusual. I know at Iowa State that just doesn't happen.
Those were the old days.
Those were the old days, yeah. You wouldn't know it, but Eddie's actually a lot older than me. So where was I going from here? Do you remember? No. I had a list of some of the important papers that he had published, and I had one of the ways that I look at, or was trying to look at how much of an impact he made on the field, was to look at how many times his papers had been cited. And a lot of people would think of having a successful scientific career as if they had been cited maybe a few hundred times over the course of their career. And Eddie actually has a paper dealing with biochemical adaptations to exercise with John Hollisey that's been cited, just the single paper, 675 times. And then he has several in the hundreds, and these are all really important studies. And I think what's also really unique about Ed is that he's published in lots of different areas. So he's done studies on the cardiovascular system, rehydration, carbohydrate and fat metabolism, and then, as he's going to be talking about today, he's also had a keen interest in looking at aspects of performance in elite athletes. And I think I've run out of things to say. But we're just really happy to have him here, and he's going to tell us about why Lance Armstrong is such a good cyclist. And hopefully during the question period we can get to the really heart of the matter, which is Lance going to marry Sheryl Crow?
Thank you, Doug. Thank you, Jerry. Thank you very much. I'm not sure whether I should be disappointed that my Macintosh computer wouldn't accept your thumb drive with some incriminating pictures, I assume. I don't know what those will be, but my computer screens those kind of things, so I think it's a smart computer if those pictures might get me in trouble here. But first of all, it's indeed an honor to come visit Iowa State University and to give the Pease Family Scholar Lecture. Following many renowned scholars, and coming to a university that has a great reputation in health and human performance and kinesiology over the years, and one of the top programs in the country, I understand, in the top 20 at least in that area. So, and also to visit colleagues that I respect and have followed their work so closely over the years. This is really an exceptional institution. Well, I'll be talking about, as Doug mentioned, something we call my fun studies, that is human performance and the putting all the pieces together in the human body, studying the various systems, and then trying to focus them on what allows endurance athletes to perform as well as they can. And we've been fortunate that Lance Armstrong turned out to be one of our subjects early on, as you'll see. So we've been studying him over the years, and that'll be the focus. And of course, it's nice where you can personify the scientific story in one face, in person, and tell that. And somebody who's been incredibly successful in sport and in life. And in many ways, I subtitled this where sport reflects life, because Lance has been through not just cycling, but a lot of life events that we all know with his cancer and his causes and all. So that's the subtitle, Sport Reflects Life. I'm not really sure if it should be Life Reflects Sport, so I kind of go back and forth. You can decide. But first of all, I'm very fortunate to have had great mentors with the lower row there, Frank Hatch and Bill Mercado being my undergraduate advisors, and they've written textbooks. And as Doug mentioned, both of us were trained by Dave Kostel at Ball State University, and I got my PhD with Jack Wilmore. And then both Doug and I received our postdoctoral training with John Hollizy, who is an MD in the Department of Preventive Medicine in St. Louis, and is the father of exercise biochemistry in a lot of ways in relation to health and aspects of human performance. It's all really the same. And then, of course, some of my best teachers have been my doctoral students and my other graduate students. These are just showing a few of the doctoral students. The few of my graduate students here, these being the doctoral students, and one noted student here is Jeff Horowitz, who's a native of Ames, Iowa, and his father has been a professor on campus here for many years, is now Professor Emeritus. I don't see Dr. Horowitz and Carol in the audience. There they are. Oh, hi. So it's good to come to the grounds where Jeff kind of got the bug, I imagine. So I'm in Texas, which is a hard thing because you notice I probably don't have a New York accent. I mean, a Texas accent. I have a New York accent. So I've been there 23 years, but I love Austin. And Austin is rolling hills and lakes, a few cowboys, but a lot of bicyclists up there. And so it's been a good town for studying endurance athletes. And I've had a long-standing interest, having been a runner in high school and college, and trying to figure out why I couldn't run faster, what the limitations are to human performance and putting it together. And what I'm speaking about applies to all of these types of endurance sports, with events lasting from 3 minutes to several hours, like you see in the competitions of the Tour de France day after day. And we can, we know our cars pretty well. And sometimes it helps for me to start out explaining, well, your body's like your car. You have the engine, and that produces the energy. And then you have the parts in the transmission, where that energy is transmitted to the wheels, so the thing moves. And to go faster, you can have a bigger engine or a better transmission, and then go to the parts of the engine and the carburetor delivering oxygen and things like that. Well, we study athletes in the same way. Of course, it's harder to, after you take them apart, put them back together, the athletes. So you can do a lot more things with cars, and cars are man-made, so we're limited in how we can investigate all those, but nonetheless we try. And we know things like the muscles are very important, and that circle describes a muscle fiber, and inside there's a mitochondria where the energy is being produced by consuming oxygen. And we study those types of biochemical processes, and knowing that having good plumbing is also important, blood vessels that deliver the oxygen, and having a lot of pipes to the muscle fibers in the form of capillaries are good. So I'm just trying to give you a feel for some of the things or the pieces we call them the morphology, the parts of the athlete we study. We know that athletes need to have, at least endurance athletes, need to have big hearts. The hearts are pumping blood and pumping oxygen, and we'll see how cyclists, and in particular Lance Armstrong, has certainly a big heart and can pump a lot of blood. So we try and understand what the individual pieces are, but then see how they fit together in the whole. And this is our model, actually, that has been developed by a number of people, and I've published a review article even before I met Lance Armstrong, making some predictions as to what all the pieces are. And on the bottom we see these morphological components that go into making the individual. I talked about the muscle capillary density, the pipes that deliver the oxygen. Stroke volume is how much blood your heart pumps per heartbeat. With each heartbeat is pushing blood and oxygen to the muscles. Hemoglobin on the bottom is the red blood cell carrying component, delivering oxygen. Aerobic enzymes of mitochondria. Distribution of power output and technique is the technique of bicycling. And then we see percent slow twitch muscle fibers on the extreme right, which people are born with slow twitch and fast twitch, and they have different characteristics. And we'll see that slow twitch link up to the functional capacity of having a high, or affecting gross efficiency, the transmission, so to speak. So the case I'm building here is that when we take the athletes apart and look at the pieces and put them back together, we try and understand how the different components fit, and how our theories are that having a high percentage of slow twitch muscle fibers may make you more efficient, and that may directly improve your performance power and therefore your velocity, how fast you can race at. So really it's an understanding of these kind of models and interrelationships that we're continuing to develop. And we have functional abilities, those are tests we can do in the laboratory. Many of you are probably familiar with doing stress testing in athletes, where you can measure their maximal oxygen uptake, or their VO2 max, the highest rate that their bodies can consume oxygen. We can measure how fatigable their muscles are by measuring blood lactate concentration and this measure of the lactate threshold. And then we have a measure of gross efficiency, which I'll be explaining. So they fit together, and of course the athletes are most interested in their performance velocity. I forgot to and they're interested in a bicycle, having good bikes so they can have a good aerodynamic position and not catch much wind and go fast. I'm not a biomechanist, so we'll kind of take that out. And performance velocity we'll take out. We'll be talking a lot about power, how many watts of power, like horsepower or watts, these athletes and Lance Armstrong can produce. So, this is a picture of Lance when he was just turned 20, and he moved to Austin, and since then he's gone on to great things in cycling, also becoming the 7-time winner now of the Tour de France. So we've been fortunate to be able to study him during a critical period of his maturation, and so he was coming into our laboratory usually in the early season before he headed to Europe in January, February, and March, and we'd make standard measurements. You can see him with the mouthpiece in. We're measuring his maximal oxygen uptake and his submaximal efficiency, taking a blood sample to measure his blood lactate levels, and heart rates and cycling cadences and all those things. So when he was younger, he had more time. He could hang out in the lab and, talk about some of these things. And he's gone on, of course, to really excel and focus on the Tour de France, make that the race that he peaks for. And we'll see that he knows how to win the time trials riding on the flat roads, but also something we never expected. He became a very good mountain climber and can ride up the steep passes as fast as anybody, certainly in the last 20 minutes, faster than anybody when it really counts. And we'll see how he's accomplished that. But this gives a little history of at least his cycling career, where at age 19 he became the youngest U.S. national amateur champion, then went on to get a cycling professional contract with Motorola, same year that he rode in the Olympics and finished 14th. He was the youngest world champion in a one-day race in Oslo, where he won it pretty much out of guts, just not knowing that he shouldn't be trying to beat Miguel Indurain, and he went downhill faster than anybody else would go, and they were afraid of crashing, and he got away. He won it on guts, certainly, but shows that's an important part of who he is. He won one stage of the Tour de France at age 23, and then in 1976 he was diagnosed with testicular cancer, and subsequently had surgery, brain surgery, testicular surgery, abdominal surgery, went through chemotherapy, and had his last treatment in December of '96. And I'll show you, we actually tested him 8 months after chemo, so I'll be showing you some of those data. Then he went on, and I think his most impressive accomplishment was to come back in '98, just 1 year after resuming training, and finishing 4th place in the World Championships, both in the road race and the time trial. That's incredible, in my opinion. And then he went on to win his first Tour de France at age 27, and then has continued for the last 7 years. Well, that's certainly impressive. And I'm asked the question always, how does he do it? How does he dominate? This just shows a video clip. Can you hear that? So it just shows Armstrong dominating Jan Ullrich, who people believe is the most gifted, physically gifted person in the world.
That's what he wanted. He wanted to catch Jan Ullrich. That was the little piece of a recipe that he needed. He needed to get out there and make a statement on day one, but to go through the 15 kilometers.
So Lance just appears to dominate, and he does dominate.
Time check, the time 16 minutes.
And the question becomes, how does he do that? And it often gets boiled down to, is he just a genetic freak? So it's amazing. We published a study on him. The media says, well, it's either he's a genetic freak, which, what is a genetic freak? If somebody can define that. He doesn't have a third leg for bicycling, or and certainly, and then they say, well, it must be intense training, one or the other. Well, it's usually a combination of a lot of factors, and that's the point I'll be trying to get into. He started training here when he was young.
Started with running.
And this is his mother talking about him.
Interesting. I look back at that time, and I mapped out a 6.2-mile course for Lance. And when he'd come home from school, he'd run that loop. And on weekends, we would go to 10Ks throughout the Metroplex. Guys I was running with, they're going to do this race over here. Okay, well, I'll enter you in that race.
Lance Armstrong lives in Plano, Texas, where he goes to high school. Yes, high school. You can see again, Lance Armstrong on the left with that striped helmet has the lead.
He was having a lot of success beating a lot of very good triathletes, even at the age of 15.
Lance is 15 years old, but is already ranked as one of the top triathletes in the country. I don't get real psychological about it. I just, like a lot of people do, they get really psychological, but I just go out and race, have a good time.
He had clothing that was supplied by the store. I just saw a kid that had some drive.
Just go in, just like I was been racing the whole race. Don't stop.
He was swimming. And Lance was competing on the swim team in Plano. And he had this great coach that was a tough disciplinarian.
I saw Lance as being a very good swimmer, and of course, that was, being my profession, what my interest was.
But Lance wanted to do it all, swimming, running, and biking. He loved racing, and Linda fully embraced her son's passion.
Linda was always his biggest cheerleader. She was his biggest fan.
So clearly he was motivated from a young age, liked to race, was a competitive swimmer, runner in high school, took up biking in high school, then became a triathlete, and then decided, well, to really make his mark, he'd have to focus on one sport. He picked bicycling, and very quickly rose to prominence in that. And certainly he has a drive to train intensely, and he's dedicated. And so he moved to Austin when he was 19, and soon showed up in my laboratory. We've been doing a lot of bicycling studies on cyclists, and Jeff Horowitz certainly was testing a lot of those individuals for his dissertation, and some of Jeff's students actually were friends of Lance, or competitors of Lance and friends, and so they dragged him in and said, we've been through this, you need to be through it too. And so Lance showed up one day, and we began to study him, and that was good.
I can push it,
He talks about his body.
study it, tweak it.
So he's focused on understanding enough, and I think all that helped. His discipline in sport, certainly helped him, I think, through the ordeal of cancer and being such a young man at your prime and being struck with that out of the blue, and gave him focus or something to return back to. Certainly when he was making a comeback professionally, and the French team Cofidis wouldn't renew his contract. So that gave him motivation, and the Postal Service then formed a team for him with a small amount of money, actually, and just so he can get back out there and prove. So we were fortunate to be able to study him during this period, and so these are the years from 1992 up through 99. You can see what his ages were, and so I'll be showing you data on time points before he won his about the time he won his first world championship, when he had chemo after cancer, when he finished 4th place in the world championships, and then eventually to his first Tour de France victory. So this is really what it takes to mature into the Tour de France champion. We really haven't had much interest in continuing to study him as in depth every year in what it takes to win the Tour de France, and he's been very busy, and so have we. But we do know that over that 7-year period that was most important to his cycling development, some things were very stable in him. Remember, he'd been training intensely since he was young, and he already had a very high maximal oxygen uptake, close to 6 liters a minute. We express it in milliliters per kilogram at 76 to 83, and those of you who know the values, those are high values. Not superhuman, but certainly high. He has a high maximal heart rate, but that has been coming down with age. That's a normal response. You lose 1 heartbeat per year as you get older, but his heart still beats maximally at over 200 beats per minute, which is pretty high, exceptionally high for somebody that large. He weighs about 180 pounds normally, but I'll show you. His lean body mass has been very constant at 68 to 70 kilograms. That is how much of his body is without. How much he has muscle and bone, excluding fat. Well, if we compare Lance to novice cyclists, good cyclists, elite cyclists, he's in a class of his own. Well, I should say he's in a very select class. But these values of having a VO2 max of 6 liters and his lactate threshold and all, we've tested 3 individuals. I've personally tested 3 people who physically, I think, are as talented as Lance. One was his teammate from Motorola, who didn't come back. Lance said he just wouldn't train as hard as he needed to. And another was actually one of Jeff Horowitz's favorite subjects. He was a triathlete, a very big guy. Was more talented, in my opinion, and a lot of other people's opinion, than Lance, as far as what his absolute VO2 max was, his efficiency, and he was incredible. So Lance wasn't superhuman in that we had seen at least 2 other people who were very similar to him. Well, these are the components that he had, and we're talking about these values over here, the VO2 max and lactate threshold being very high, well developed through his early years of intense training. And his performance VO2 is high, but his gross efficiency, we'll see, was not very good. And what we're talking about is he was a young kid who had a big engine. You know, he had a lot of raw ability to produce raw power, and we physiologists measure raw power chemically in your ability to produce adenosine triphosphate chemical energy. Then the question is, how smart are you, or how efficient are you at using that energy? How much of that gets converted to power, and how much is wasted and goes to heat? We'll see only about 20% of the energy from ATP hydrolysis of the raw energy goes into powering the bicycle, and the vast majority goes off to heat. By the way, humans are much more efficient than your car at doing all that, and even though it's you may think 20% is low, that's still a good number. But Lance was not very good at this energy transmission here early on. And what it comes down to is we believe that, and we call this efficiency, the efficiency with which these are the actin-myosin filaments, the protein filaments in muscle. So this is the motor. This is the motor in the muscle, essentially, where the ATP combines, and then that energy is used to slide the pistons, essentially. These are the pistons in the muscle. And the question is, how much power do you get out? And as I mentioned, muscles are, on average, 20% efficient. 20% of the energy gets converted to movement, to power. And slow twitch fibers, it's a type of muscle fiber that people have. Most people have a mixture of slow and fast. We'll see an average person is 50% slow, 50% fast. And we think that's changeable with training. We certainly think efficiency is changeable, as we've shown with Lance. So we'll be talking about these processes. Well, we've been able to measure this in Lance, this measure of muscle efficiency over that 7-year period. And we see that he's gone up in a straight line, just a linear increase over that 7-year period in efficiency. What I'm talking about is when he first started, his efficiency was down here around 21.5%, and it increased progressively over the years to over 23%. And in absolute terms, that represents an 8% improvement. Well, 8%'s a lot. When you start talking about 1% separating champions from also-rans, somebody who can improve how much power their muscles are capable of generating, simply by their muscles becoming more efficient due to the chemistry, that's a huge improvement. So he was able to get 8% more watts of power out, and you can see here it was a progressive increase. And we've asked ourselves what we think that's due to. Unfortunately, we haven't done a muscle biopsy on Lance, although he agreed to do it way back when he was younger and we were all set up, but we didn't have institutional review board approval. So we had to wait to do that, and he went off to Europe. So every time he comes in, it's like, oh, we should have done that. And so we regret not doing that, and hopefully we'll do one now, or when he slows down a little bit and spends a bit more time in Austin. But we've done that prior to studying Lance on a number of elite cyclists. And actually, this is a study from Jeff Horowitz, who was the first author on this study, where we had a group of cyclists who are mostly slow twitch muscle fibers compared to those who are average 48% slow twitch. And they can exercise at the same rate of oxygen consumption or bodily energy expenditure or heart rate, same level of exertion. But subjects who have more slow twitch produce many more watts of power although they have an equal VO2, their power output is improved by 9%. They can bicycle for 1 hour, 342 watts. Maybe knows watts. They'll appreciate these numbers. Compared to the average cyclist going at 315. So these individuals are identical in every way except their muscle fiber types, and having more slow twitch allows them to be more efficient and produce 9% more cycling power. So that's a big effect. When we study populations of bicyclists, we see that there's a big range, a 20% range, in what their efficiencies are. Some people are around 18% efficient, others are around 23% efficient. That means that everything being equal, when they're riding down the road, some people can go 18 miles an hour, others can go 23. For the same level of bodily exertion, of the energy their body's exerting, some people are more efficient at converting that into speed down the road, 18 miles an hour, 18% efficient, others are going at 23. That's a big difference, which we see is directly related to your percentage of slow twitch muscle fibers. So, the question, it's an advantage to be a high percent slow twitch, and the question becomes, can you change that with training, or is that a matter of genetics of what you're born with? And we don't have an answer to that, because if you can change muscle fiber type, it takes years of intense training to do that. There's some studies in rats suggesting you can accomplish something like that with chronic muscle stimulation with an electrical stimulator 20 hours a day for weeks or months. Well, who comes closest to stimulating their muscles for hours a day but a bicyclist riding 6 hours a day over 7 years? So this is as close as you can get in a human model. And what we think is that it agrees with our ideas. We haven't proven it because we haven't done the direct muscle biopsies on Armstrong. But it seems as though that Lance started with only an average efficiency and an average percent slow twitch, starting right here. And we believe that he was able to move up throughout the years. He certainly, we have reported he directly increased his efficiency right along this line from 20% to 23%. And we predict that he improved his percent slow twitch from 50 up through 80%, which is certainly reasonable within the range. We know for sure he's improved his muscle efficiency. That's something we've directly measured, and that's what's most important to the functionality of bicycling, regardless of what we conclude scientifically or the mechanism. And we can't conclude directly with Armstrong, again, because we didn't do the muscle biopsies. But we do see in a population of bicyclists that we've studied, we see this relationship that the number of years that they train, you see a direct relationship with percent slow twitch. The greater number of years that you train, the higher your percent slow twitch. So this agrees with the idea that you can change it. However, it's a classic chicken and egg story. Who's to say that maybe it's not that you can change fiber type, increase percent slow twitch with years of training? Maybe the others, that having a high percent slow twitch makes you more efficient. If you're more efficient, you're more successful. If you're more successful, you get your cycling contracts renewed so you stay in the sport longer. Yeah, so we just can't say which is which, so we have to be open to both possibilities. But if you can change fiber type, and we were guessing what Lance would do, he would fall right along that line, starting out here, and with the number of years of leg training, and then moving up to here. We first started him, he had 6 years, and then he went on, but toward the end he had accumulated 13 years of training. So it fits the story. Well, another thing that's changed remarkably is his body weight. And we measure that in kilograms. And you can see here that when he was younger, he was around 78 kilograms. That's about 180 pounds. And then he would race at about 76 kilograms, 176 pounds, somewhere within that range was his normal body weight. And when we studied him 8 months after chemotherapy, you can see his body weight was back up to where, to a healthy level. He did lose weight during chemo. Chemo certainly is a stress on the body, as you know. But 8 months is long enough if you eat well and exercise as he was doing to recover from the acute effects of chemo, and the cancer had not returned. So we found he was perfectly healthy at this point in time. He came to us wondering if he could ever return to professional bicycling. As you might imagine, there were a lot of unknowns he had to deal with. The chemo had affected his lungs, his heart, and it's hard to believe when you're that close to death. You just can't be told, yeah, you're okay, go back to it. He had to be dealt with like an athlete who had a career-ending injury, and as to whether he could really return to it. And certainly cycling was his life, and a very good way to really grieve the cancer also, I think, is getting back on the bike. We thought he should go to a psychologist, and we set up for him to go to a sports psychologist. And he just said, he just the hell with it. What do you mean? I don't need a stinking psychologist. So he just got on the bicycle. Unfortunately, he went on to win and all. If he didn't win, then he would have needed a psychologist to bring him back. No, I'm serious. But so he was fortunate there. But the point is that post-cancer, his body weight returned to normal. We found his lean body weight, how much muscle mass he had returned. And sometimes you hear that cancer did something to him that made him different, reduced his body size, that made him a better hill climber and all that. And we see no evidence for that at all. Cancer had we couldn't see any effect, negative or positive, of cancer on his body. But what he did learn is that to win the Tour de France, out here when he was racing the Tour de France, he was heavy, and he just couldn't climb the mountains. It doesn't take too much scientific thinking to know that if you can reduce your body weight, he's losing 10 pounds, or about 5 kilograms, 10 to 12 pounds. Okay, so he lowers his body weight by 10 to 12 pounds in the months prior to the Tour de France. 10 to 12 pounds. That's a huge amount. That will help you tremendously in climbing those very steep mountain passes. These cyclists are looking for ways to shave their bicycle and lose an ounce or 2 ounces, spending hundreds of dollars or thousands of dollars in technology. He's losing pounds, tens of ounces, hundreds of ounces, in his body weight. And of course, that's going to have a big effect, to the point where when he won his first tour, he was down to 72 kilograms, about 154 to 156 pounds. So extremely lean, and he reduces body fat levels from 10% down to very low levels, just 1 or 2% probably. Well, is that magic? Is that secret? What was his secret for losing body weight? He went hungry. He went hungry in April. That is, the tour goes on in July, and for the early part of that season, by the way, body weight does come back up to 178 off season. He says it doesn't. You put him on the scale, and he says the scale's not right. I'm not that heavy, but he loses it. So he did that again this year. Didn't quite lose as much weight because he didn't have to. So a combination of increased efficiency and lowering his body weight. He's increasing his efficiency 8%. He's lowering his body weight 8 to 10%. Well, when you put the two together, if we calculate how much power he has per unit body weight, power per kilogram of body weight, over the course of 7 years, from the time he first rode the Tour de France and wanted to win it, he improved his watts per kilogram 18%. 8% increase in efficiency divided by an 8% improvement in 8 to 10% reduction in body weight. The two summate to an 18% increase in the quotient, that is the watts per kilogram. That is huge. That is incredible. Again, when you talk about athletes succeeding based upon 1 or 2% differences, he improved 18%. And that's simply due to muscle changes and to losing body fat. Okay, those are the two components that go into it. So that's incredible, and we think, weighing 71 kilograms, that he can ride at 500 watts for at least 20 minutes. He thinks an hour. I don't think he can go an hour. But 480 for an hour maybe. But anybody who's a bicyclist and knows watt meters, and a lot of bicycles have these on there, that is an incredible power output. And so he's setting the standards for cyclists now talk about how many watts per kilogram can you maintain for just a couple of minutes, you know, and he can go with this for 20 minutes, 7 watts per kilogram. So, you know, we see that in essence, you know, Lance started young and improved his engine and his VO2 max, and he was only average in his efficiency, and that was his weakest link. And so he really improved his weakest link tremendously, and then also reduced his body weight. And those two factors are what really propelled him to be the Tour de France champion. And he's gotten better at riding a bicycle and reducing resistance to movement with his aerodynamics, and that certainly helps in his performance velocity. And you know, there are a lot of other things in the sport of bicycling that go into it. Cycling is Tour de France is very much a team sport, and you can see that in this video.
This is a powerful squad. I know Team CSC really believes that they've got the strongest squad ever, but I think this squad on paper is the strongest squad that US Postal now.
This is the Discovery team.
Fielded at the Tour de France. I mean, you're looking at guys who are capable of finishing in the top 5 in the Tour de France on their own. If you take Azevedo, if you take Beltran.
So they're riding a team time trial, and they go into pace line, and each cyclist takes a turn, and they won the team time trial very impressively.
Jaroslav Popovic, and many people believe that man there wearing number 7 is the future of this squad. After all, you know, he's finished 5th and 3rd overall.
And it's likely that probably, I think at least 2 of Armstrong's teammates on Discovery Channel, maybe even the Postal Service, if they were told, you're going to be Lance Armstrong, you're going to be the leader of the team, we're going to protect you, they could have won the Tour de France also. Because the team's job is to make sure that Lance doesn't have to expend any energy, that Lance rides in their slipstream, in their draft, and that they bring him food, they make sure he's rested, he's protected, until they get to the steep mountains, and then they let him go. And so he's rested, the team gets him there rested, and his job is the last. The Tour de France comes down to essentially riding up 3 or 4 steep mountain passes during the last hour of the race. It's a 5-hour race. You get to the bottom of the mountains, and then the last hour, you wait for somebody to try and break away, and then you make sure you get to the top first. It comes down to who can ride the fastest for about 20 minutes. And Armstrong's team makes sure he gets to the bottom of the mountain rested, and then he's ready and confident he can ride up that mountain faster than anybody for 20 minutes. He does that 5 times. That's how he wins. He also rides a good time trial by himself because he's big enough, and his team rides an excellent team time trial. And you put that together, it's just a winning formula. So the teamwork is very important. And so he's really developed very specialized training also. And it's incredible in the Tour de France that some people ask, well, how does he dominate his competition so much? And part of it, I think, is that the competition may still be in the old school mentality. And I say that because I still don't understand why his main competitors, like Jan Ullrich from Germany, and rides a Tour of Switzerland in June. The Tour of France is in July. And Basso rides the Tour of Italy. He's Italian, so that's okay. He rides the Tour of Italy right before the Tour de France. How can you do that? I mean, you're going to start the race very tired, exhausted. Well, that's the way they've always done it. Well, that's a good way, maybe, when you're a young cyclist, to prove that you can suffer, to learn. Yeah, I mean, that's part of it, right? Being young, don't you have to? That's the lesson of life. When you're young, you suffer. You learn what mistakes not to make. You get out there and you do it. But then as you get older, you learn to choose your battles. right? You become smarter, you become wiser, more efficient. You save your energy. You let other people help you. You say, yes, I need your help. You lead a plan. You have a plan and you change. You do things differently. Things that keep you at the top and get you to the peak aren't the things that propelled you on the early part of the journey. That's a part of how I think sport reflects life here, and Lance has been, although he's stubborn and bullheaded, eventually he gets it. And one part he got was the importance of doing interval training. That is, resting for a few weeks before the Tour de France, focusing on doing intervals to ride up those steep mountain passes. And his teammates, Hincapie and others, were doing the same. And they were having fun in the Tour because they weren't tired. They didn't start tired. They didn't start overweight. And they had a plan. And I think they made it look too easy, frankly. Well, finally you say, when you take the model and you boil this down scientifically, what does it take to be a Lance Armstrong? Does it take somebody to be a genetic freak? Again, I don't think so. If we take the initial components I started with, the muscle capillary density, the parts of your body that put you together, your stroke volume, your hemoglobin, enzymes, and we'll see that if you are an individual who becomes a competitive cyclist and trains hard, if you're the best out of 10, 1 out of 10 in capillary density, that's not freakish or superhuman, you're the best out of 10. The best out of 20 in stroke volume, the best out of 2 in how much blood you have or hemoglobin, the best out of 5 in those. But you don't really have a weak link, but you're not superhuman. If you put those all together, the probability is, if you multiply 10 times 20 times 2 times 5, that's 2,000. That means you have the best out of 2,000 in VO2 max, the best in your high school, big high school. And then you add that with a good enzymes, and you're best out of 20,000, and best out of 200,000. And Armstrong's improved his weakest link, efficiency with training, become 1 in 500. And you add all these probabilities together, they just add up to a person whose performance is 1 in a billion. This is not scientific, this is my estimations. So I haven't done the population studies to get the distribution, and I've tried, but again I gave up. But I think this approach should be taken, and the point is that you can identify young talent, you can see how the pieces are put together, and you can decide, well, you're balanced here, this is really good. To improve, we need to do this, and this is the type of training you need to do, and this is when you need to take it easy. And so I think we have enough of that understanding to really begin to apply this to individuals in their training, rather than individuals having to survive the system. Too much of the coaching is the athletes survive the coaches in the system, and there's not enough change depending upon what types of adaptations they need and where they are in their career. And the final point is, what my final message, and as you know, we're talking about physiology, but also Armstrong is a true competitor in that he lives to compete. He doesn't just like to win, he needs to win. It's his identity, and I believe what you see on television and what you read in the books, he's an open book of who he is, and what you see on his face is exactly, as much as anybody as to who he is. And this is just one video clip where he fell in 2004.
I saw it coming, and I said, shit, I'm gonna hit this thing, and just caught the end of the handlebar, and there's nothing, somebody's holding on to it, and it's holding on to your handlebar, you go down, and so.
Then he slipped after that.
Tyler kind of went to the front, and Urakan in this tour, and don't forget, he hasn't lost it yet. Then I think today he'll be remembered for his fine gesture of sportsmanship. Okay, Lance Armstrong leads the Tour de France. That's the big news by 67 seconds. We haven't finished yet.
Yes, we have finished yet. So that's, it's a combination of factors. It's no one factor. It's certainly he had a genetic head start. He nurtured that with years of intense training. He modified his training and trained smarter to focus on that one race. And he did things like losing body weight, specifically for the were riding up the steep mountains, had a great team, and those are the components that really launched him to what we see here. I don't see it being freakish. I see it being spectacular, a good story, but you can see it's a kind of a team community effort that has launched him. And I think his missions in life now are focused on taking the same philosophy to his cancer foundation, to the Lance Armstrong Foundation, the Live Strong movement. So that's, I think, where we'll see his energies focused next. Thank you very much.
What a wonderful lecture and description, stay up with me, Ed, of the scientific adjustments of Lance Armstrong's training protocol and the effect it had on his improvement and becoming a champion cyclist. At this time, I want to present Ed with a little plaque, which depicts him as the Pease Family Scholar. And also, we keep one in the office that he's listed on. And so I'd like to present that to you, Ed. And that's something he'll have around for a long time. He may make quicker use of this, which is a gift from the endowment for your presentation to us. We appreciate very much the fact that Ed will come in and spend several days with us, with our faculty, with our students, in addition to giving this public. We benefit tremendously from having scholars like Ed here with us. And so we really want to thank you for that. Now, we do have a few minutes, and I would guess there might be a question or two. And so Ed would, I believe, consent to try to answer a question. If you'll stand up and speak loudly, and then I'll try to repeat your question.
Okay. Right after the Tour de France, there was conjecture that the athlete winning 7 is going to be broken faster than most people think because of becoming more specialized. And actually, the trend, if you look, is to win more of them strung along year to year. Is this what you're talking about possibly with the focusing in just that one area and improving everything the science is going to allow it to happen faster and faster?
Yes, the question is, in sport there tends to be more specialization these days. Maybe Armstrong's an example of that. He's focused on the Tour de France, and has that kind of thinking, along with science, allowed somebody like him to do that, to pick one event and say, this is mine, and I'm going to focus on this exclusive of other races, and win that year after year. Is that correct?
I just want to know if you thought that it was going to continue that way, with more athletes being able to do 8 instead of the 7 that it is right now, or other sporting events.
Well, I think Lance is ahead of the curve, and he's identified the Tour de France that he wants to focus on and specialize in. Remember, all you need, if you have 10 individuals who are equally talented and they all say, I want the Tour de France, then it's going to be 10 people doing it. Then there's going to be more competition for that one spot. So it's hard to say. And the sport of bicycling is going, since he's dominated the Tour de France, if you follow cycling, they feel that cyclists should be like cyclists of the past, who focus not on one race but 3 or 4 races throughout the year, and that he's not playing by the unofficial rules. Is that just not pick one race and dominate it? You need to suffer through the entire season and see who can last the entire season. So that's still their thinking. So they have point system now, where it's when you ride the Giro, another tour, and a tour of Italy, that you accumulate points, so they have an overall kind of, season yearly winner. So yeah, I think that means that there are just different ways you can give out medals and recognition.
Yeah, the point you made on the radio show about playing to the audience with the Tour de France, with the American audience and the Europeans.
Yeah, a point Jerry just mentioned this morning on radio, we got a similar question, and I think Lance identifies that cycling isn't appreciated as a sport in the U.S. It certainly hadn't been before he was riding. It was relatively unknown. Certainly Greg LeMond did a lot for it. And the Tour de France was about the only race that Americans knew about and got excited about. So by Lance dominating the Tour de France, he's really brought the sport of bicycling to America. You know, if Lance were winning occasional races here and there, he could have gotten recognition in Europe that never would have really translated here to the U.S., which was his main interest of doing that. So his focus was on bringing bicycling to the U.S., picking the Tour de France. That's the most important single most important cycle race, and dominating that year after year. The Europeans have a different philosophy. So it, again, depends on which side of the Atlantic you're on. I think both sides have valid points.
You said his weight loss didn't matter in the last year. I was wondering if you could expand on that.
Well, I might have misspoke there. His weight loss didn't matter. He has lost weight. His weight in the off season does go back up to 175, 178, but he gets that back down to 160, 158, 160 during the 2 or 3 months before the tour, and he does that every year. He has done that every year. He said he'll never have to do that again, but he does that every year, and that certainly helps. But his weight loss after cancer, his acute weight loss after chemotherapy and cancer, really had no long-term effects.
Yeah, they also, during the tour, they made a big to-do about differences in lactic acid production, recovery time, that he might be better than this. Is there anything to that, or is that all just sort of media stuff?
The question is, during the tour they made comments about his low blood lactic acid levels and quick recovery. I think there is something to that. We've seen that Lance's blood lactates are the lowest we've ever recorded at the end of maximal exercise. They're in the range of 5 to 7 at highest millimolar concentration. So, and that's after going at 580 watts to fatigue. But when he detrains, when he was reduced training after chemo, they went up to 9 millimolar, which is close to normal. So what I'm saying is I think he has those very low blood lactate levels because of his intense training. And maybe there's a genetic predisposition to turn off muscle glycogen or phosphorylase, and Doug and I can talk about a number of things that might be going on. But so I don't think, however, I got a question from Nature, some reputable journal, saying they were investigating, well, Nature's reputable, yeah, saying that they were investigating claims that he has an allele of a genetic mutation in his muscle for lactate dehydrogenase. And there are a lot of stories floating around. There's no credibility to that. It might be possible, but nobody's ever done the sampling to do that. So, but you hear a lot of things to try and account for his dominance.
I don't know if this is measurable, but it seems to me that pain tolerance is a factor in how well these endurance athletes are able to do. Is that ever measurable, or
Yeah.
what have they thought about on that?
The question is, pain tolerance is a factor, and it certainly is. I think all of these professional competitive bicyclists, however, got to a point where psychologically they can push themselves to the point where their bodies give out. The sport kind of self-selects there. I'm not saying psychology doesn't have any role, but at least the ones who are at the very top, when they crack on the mountain passes, and they're cracking because their bodies can't do it. Most of the time. I think some of the times, however, they drop out of the tour later because the chronic fatigue and not sleeping and things like that accumulate. But when you see somebody crack like Ulrich, it's the body, for the most part. Yeah, Jerry, you want to pick somebody?
Sure, come back here.
Is there any correlation between age and with fast twitch muscles and slow twitch? Do you change
Yeah.
in age?
Is there any correlation with age and percent fiber type slow twitch? You seem to increase your percent slow twitch with years, with aging. And Doug, and you lose fast fibers. Maybe, we don't know, maybe because you're not using them as much. but certainly there's a tend to get more slow twitch, and that's never been looked at as to whether that makes you more efficient, because you have to study the same people for long periods. But it might not be part of the wisdom. Your body gets wiser and uses its resources better as you get older. Well, those are both very good questions. First of all, and the first one, yeah, I think you're correct in that the successful ultra endurance triathletes are older, and again, we haven't directly shown that in one individual that, like Lance, that you do change your percent slow twitch. We're just showing that he increases his efficiency, and we think that's because of that. So that needs to be determined, but certainly, that would agree that training is almost like accelerated living. That is, if throughout the course of your life, you tend to develop a greater percent slow twitch, for whatever mechanisms. I'm not sure why they are. Maybe because you're losing fast twitch, and so all that's left is slow. That's not a healthy way to do it, but a healthy way to do it may be here with training. And that certainly, at least in Armstrong, had the effect of increasing his efficiency. The second question about, he recovers so well, and if he produces less lactic acid, and if he does indeed, if his muscles don't burn as much, essentially produce as much acid, is he doing less damage to many of the chemicals in his muscle? Including the, yes, especially the ATP, and they can be degraded, and you can, it takes a longer time than just 20 hours to recover those nucleotides in the muscle. So that's a good possibility, and I don't know, Doug, Dr. King's done some of the acid-base balance in muscle, and has ground up muscle, measured pH and some of the proteins. So he's the expert in that. Dr. Sharp.
They're passing
Oh,
it off
Dr.
on
Sharp.
you.
I'm not gonna
No, Dr. Sharp, yeah.
Another question? One over here.
Yes, you mentioned multiple times how he developed his engine as a young man. Have you done studies on other children, perhaps, at that young age in developing that engine, and then see what happens to them as they age, whether they continually develop that? Do they ultimately lose it if they don't continually use the engine and develop it, or?
Yeah, that's a good question. I haven't done those studies on children, or, you have to, of course, factor in the growth process, study them before puberty, and there have been some studies that have attempted that longitudinally in freshmen in high school and following them through their senior year when they compete in track and things like that. But there haven't really been enough subjects in those studies to come to conclusions as to how much, maybe the kids who had hearts that were going to grow bigger joined track because they were successful at it. So I'm not familiar with any definitive answer on that, but I do believe that there, I would hypothesize, just guess, that it's important to train intensely in certain growth periods, maybe in puberty, where your heart and blood vessels are more adaptable to stretch, and maybe even the pericardium, the connective tissue surrounding the heart. So I think there may be some advantages of training early on, but I'm not advocating adolescent training or starting as early as Armstrong did there.
Can you compare running and biking in terms of increasing this muscle efficiency. I'm thinking in terms of the fact that biking, you have to just be on the bike for such a long time. Most of us don't have that much time. We're not professional with it.
Right.
And can you achieve greater efficiency faster by running than, say, by cycling?
Again, this is, our report in Armstrong is the first published paper suggesting that you can improve efficiency with years of training. Before that, people were saying efficiency is something you're born with and you can't change it. So again, we need more studies to verify this first observation. The only data I know of is I was in England last month, and I actually gave a lecture, and on the program was Paula Radcliffe's coach, and he's an exercise physiologist, Dr. Jones, and he has measured Paula Radcliffe's economy. Paula, by the way, is the women's world record holder in the marathon. I forget, she ran 2:15, was it recently? In the World Championship, she ran, in this last summer, she ran 2:15 marathon in the World Championships. So blew away the women's world record. And he claims that her running economy she's 30 years old now, from age 19 through 30 has improved 20%. Just, when I looked at that, it was just incredible. And he has the direct data, and he's a very careful scientist. So those are the only other evidence I know that that economy can change, or efficiency can change, in running in this case. But again, it was measured over very long periods of time. So I think we need to rethink that. She's a marathoner. Runners can't put in 6 hours a day running. So I don't know if it's a volume effect or what. So we have to be careful not to advocate, go out there and put in hours and hours, and that's going to be counterproductive. So I also wonder why swimmers put in so much time in swimming when their events are only 1 minute long. So many of their events are 1 minute long.
One last question right here.
I just wondered if I understood you right, how you measure the percentage of slow twitch. Is that through biopsy only?
Yes, the only direct way you can do that is taking a piece of muscle, small piece of muscle, from a biopsy. So that's the only way you can indirectly predict it. We do it in cyclists we back extrapolate, we measure their bicycling efficiency and then predict their muscle fiber type. We also have power tests. We can measure what when they reach maximal power sprinting on the bicycle for just a couple of seconds, the subjects with a higher percent fast twitch reach their maximal power at higher cycling cadences. So that's a very good predictor of fiber type. You can do leg extension power. So we kind of, for practical purposes, you can back extrapolate. And if you don't want to do that, you can go to a high school and do like my high school coach did. First day of practice, everybody lines up and runs a 100-meter dash. And if you're slow, if you finish in 15 seconds or lower, you're a distance person. And if you're really fast, well, you're a sprinter, and that works pretty good too. So.
Thank you, Eddie. By the way, you've heard Ed mention several times about muscle biopsies. Dr. Sharp and Dr. King both do those. The needle is about the size of my little finger, but if you're looking to volunteer, I'm sure they're looking for subjects. Yeah, exactly. We really appreciate all of you coming. We're going to have a little reception over here. There's some fruit and things to drink. We invite you to stay and visit with Ed for a while. And ask any other questions